Okay, good morning everyone. As Kobe said, I'm going to talk about high-frequency circuits, specifically nanoscale CMOS technology. What I'm going to talk about are three main topics. One of them is trying to introduce to you CMOS technology and its tremendous scaling trend, which brings us to the topic of this conference of nano, because CMOS has been in that range for some time and continues to improve. And I'm going to talk about the opportunities that these nano devices offer, but also about the challenges that they offer for at least some of the applications of these transistors. And I'm going to talk about one solution or one proposal to a solution to one of these problems, which is called RF interconnect. And then I'm going to talk about some ideas that we have for reconfigurable devices and circuits that use CMOS technology and nanoscale devices, and the potential that they offer for future systems. So I guess that some of you are familiar with silicon and microelectronics and CMOS technology, and some aren't. So maybe I'm going to say a few words. This is a more classical view of CMOS technology, where you have an NMOS transistor and a PMOS transistor based on a silicon substrate, N plus implantation here for the source and drain of the NMOS, P plus implantation for the PMOS device. Here in the NMOS device we have conduction of electrons controlled by the gate voltage, and also here in the PMOS device we have conduction of holes using the gate voltage, and this whole thing here that you see here is what is called the CMOS inverter. That is the basic digital element in computers today that is used to invert the digital signal of 0 to 1 and 1 to 0. And this is how it looks from a top view. And these are some, I would say, more modern devices, more scale devices that use slightly different technology, but still based on silicon technology. You can see some changes. The gate and the source and the drain are not just the silicon. They're also silicide to make the resistance contribution less dramatic. You have the shallow trench isolation and also other things. What we see here is the cross-section of these devices. And you can see the different cross-sections between technology nodes. In CMOS technology is defined by nodes. This is 250 nanometers or quarter micron, then 130, 90, 65. Usually those technology nodes are defined by a factor of 0.7 from generation to generation. And the number, what it means, it's not exactly the length of the transistor channel, as some people think, but it's more likely the half pitch, which means that if, for example, we have two polysilicon lines at minimum feature size, it means that the pitch is going to be, for this case, 230 nanometers. The channel itself is usually even smaller. You can see here the 50 nanometer scale. The channel in this case is even less than 50 nanometer for this 65 nanometer technology node device. And this graph shows perhaps what you can't really see here in this picture. It's the actual oxide thickness, which is much smaller. So you see that, for example, for this 65 nanometer device, this is something like 1 nanometer thickness. So these transistors are well into the nanoscale region of operation. And the technology follows a trend, scaling trend, from 1 year to the next. So probably commercial 22 nanometer devices are expected in the market, in the computer, in your laptop or whatever, about 5 years from now. So this is more like a projection that is perpetuating itself. Okay, so first of all, what is the motivation for this scaling? Why do we want smaller and smaller devices? Then we can say a few words about that. If we have smaller transistors, it means that if we have a chip with a fixed size, let's say 1 square centimeter, we have more transistors per chip, so we have more functionality per cost. So this is one motivation. Another motivation is that if we have smaller transistors, it means that we have faster transistors because of the shorter dimensions. And as a result, we can have higher performance digital circuits. At least this was the paradigm for many years. And also, if we have smaller transistors, we have less energy consumption per operation, which is also very important, especially nowadays. Okay, so you can see some of the implications of scaling using the known Moore's law. So you can see that from year to year, we have more and more transistors per chip. So even a few years ago, we already passed the 1 billion transistors per chip, and it still continues to grow. And you can also interpret the scaling in terms of the speed of the transistors. So you can see, for example, that and this is characterized by the cutoff frequency of the transistors or the maximum frequency that these transistors can operate, and this is in the hundreds of gigahertz range nowadays, and of course continues to grow into the terahertz regime. A few more words about CMOS technology. It's not just about transistors. This is a typical cross-section of the process that usually includes something like 10 metal layers that are used in the interconnects between all those devices. If we want to have a billion transistors on a chip, then of course we need to connect them. And 1 metal layer is of course not enough. So this is more or less a distance or a height of something maybe like 10 microns that is used by all those metal layers. Okay, so we have a lot of benefits from scaling, but let's talk about maybe some of the limitations. And this is one of the main limitations nowadays for performance, of using scaling for performance increase in digital circuits, and this is power. We can make transistors go faster, but as a result, and we have more transistors because they're smaller, but as a result, we have more power dissipation, and power density is really a problem. So you can see how with technology, we get a higher and higher power density until it's really becoming inhibitive. So it has to stop, and recent years have shown that. So this is one limitation, and as a result, people are not increasing the frequency in digital circuits anymore, but rather use parallelism, as you can see here. So this is kind of a network on chip, a network of many processors on the same chip, in this case 80 of them. So what happens is that we want all those processors to work at the same time and do parallel work, but it also means that they have to communicate very fast. And the data rates that are supposed to travel across this chip are very high. And this is a problem because we want to have a lot of communication going on inside the chip, and therefore performance is going to be limited by communication efficiency and not necessarily the speed of the transistors. And why is that a problem? It's a problem because transistors benefit from scaling, but the wires do not. They suffer from scaling. So you can see more and more latency in wires across the chip as we go from one technology node to the next. So we can't use wires the way that we did because the latency is going to be too high, communication is going to take too much time, and we can't really get the performance boost that we want. So, and this is really a waste because we have transistors that are very fast, but we can't have data rates that are very high because of the wires. So what what we are actually proposing is to use RF techniques for that. And instead of using the simple voltage signaling, it's to use electromagnetic waves that travel at the effective speed of light, something like 10 picoseconds per millimeter. And we can use those transmission lines to transmit multiple waves, each of them modulated, in order to achieve very high data rates and low latencies. So this is an illustration. We can have a transmission line on chip or off chip also, and use a carrier frequency, modulate the data, and then demodulate it on the other side, so that we can get the information from one side of the wire to the other side. But we can do that for multiple frequencies, as you can see here. So this is kind of a multi-band FDMA, if some of you are familiar with those communication concepts. We can have multiple frequencies, carrier frequencies, each of them modulated with a different data, all of them transmitted on the same transmission line and then demodulated on the other side. And then we can use a very wide bandwidth of frequencies to transmit all those data streams. What we can do with that, we can use the network on chip concept that I've shown before with 80 cores. In this case, well, it's maybe 64 cores. And then we can use some kind of a ring structure, for example, for this transmission line in order to add and drop data transmissions from one corner of the chip to the other, and then cut through the traffic of this network on chip that can be congested and can be very slow. Okay, but can we actually do that in CMOS technology? So maybe some years ago, people thought that perhaps CMOS can be used for the more classic wireless frequency around the gigahertz range, but this is not enough bandwidth for what we want to achieve. So we need millimeter wave CMOS circuits if we want the very high bandwidth. We want to transmit a lot of information. And it can actually be done. This is an example of a 324 gigahertz frequency generator in 90 nanometer CMOS technology. And as a result, we think that we can actually do those kinds of circuits, as we see here. But another problem that we have is that our concept relies on the fact that we generate a lot of carrier frequencies in order to modulate each of them with data. So how do we do that? The traditional way of generating frequencies is generating each frequency and then locking it to some source using a phase lock loop. But this is a very expensive solution, and we want to generate a lot of frequencies, so it's going to cost a lot of silicon area and a lot of power. So what we propose here is to generate all those frequencies together using a multi-band synthesizer with one reference frequency. And the principle is something that, well, you've also seen some of that in Adi's talk, the concept of generating harmonics, second harmonic, third harmonic. So it can also be done electronically. So we can use some nonlinearity to generate from the 10 gigahertz. We can generate 20 gigahertz, 30 gigahertz, 40 gigahertz, and so on. But usually those signals are very low. But what we want to do is to use those signals in order to lock independent sources to the specific frequency that we want. So this is a concept of what is called injection locking, in order to lock each of those independent sources to the harmonic that we want to use. So this is what is illustrated here, simultaneous subharmonic injection locking in the millimeter frequency range. This is the concept that we're talking about, some master oscillator that controls each of these slave oscillators that are centered around harmonics of that fundamental frequency. So this is an example of that. We have a 10 gigahertz reference source, and we use that in order to lock simultaneously a 30 gigahertz oscillator and a 50 gigahertz oscillator at the same time using this subharmonic injection locking. Okay, so this is the next step, and this is actually trying to transmit data using this multi-band communication. So what we have here, we have the transmission line. This is the transmitter side, and this is the receiver side. What we have here is that we have a 30 gigahertz source that is modulated in this simple ASK modulator, amplitude shift keying on and off. And we have a 50 gigahertz source that is also modulated, and we also have baseband data. I mean data that it doesn't use any carrier frequency, it's just being transmitted across the transmission line. And on this side we have the mixers that demodulate the data in order to retrieve the data in all those three bands. So this is the implementation of that chip. This is the transmission line here, this is the transmitter, this is the receiver. And what we see here are some data streams that we get from the output. You can see that we can decode all those modulated information in the baseband, in the 30 gigahertz, in the 50 gigahertz. And this specific chip achieves an aggregate data rate of 10 gigabit per second on that transmission line using those three independent channels. Okay. One point that I wanted to mention is that this solution we think that it's good for future digital processors because it benefits from scaling. If we have better scaling, we can have higher frequencies, we can modulate faster, we can use higher frequencies, and at higher frequencies, our circuit actually becomes smaller, so we consume less silicon area. Okay, and this is some comparison with alternative methods. What I also wanted to say is one of the important things that we see nowadays is that if we want, for example, to have multi-band communication, and also for other systems, one of the most important features that we want is reconfigurability. For example, we want a circuit that at some point would work at 30 gigahertz, at another point would work at 50 gigahertz or 100 gigahertz. How do we do that? So we need some kind of reconfigurable methods and devices that we can control to reconfigure our circuit. And the question is, how can we use nanoscale CMOS switches, I mean the transistors that we use are actually switches, in order to do this kind of reconfiguration? So I'm going to give you a few examples of what can be done. So the first concept that we can use is the concept of artificial dielectric. It's an old concept. It's been used it's I think 60 years ago, something like that, to reduce the size of antennas. And the basic concept is to embed metal structures within a dielectric material in order to change, to create electrical dipoles, and then change the effective dielectric constant, and to get a boost in the dielectric constant of the material. So this is the basic concept. So how can we use that within a CMOS process and within devices such as transmission lines that we have in a CMOS process? So this is a transmission line. And what we can do is that we can embed these floating metal strips underneath our transmission line in order to form those embedded dipoles and then increase the effective dielectric constant that this transmission line sees. Okay? So if, for example, this floating strip would be continuous without that gap, we would get an increase in the effective dielectric constant without changing the magnetic properties of the transmission line. And by embedding that in CMOS technology, we can use the CMOS switches that we have, the transistors that we have in the process, in order to control if we want those metal strips to be closed or open. Okay? So we can have, if it's open, then it means that there is no boost in the dielectric constant. If it's shorted using the switch, then we can have a boost in the dielectric constant. What's the benefit of this control of dielectric constant? We can, for example, use that as a phase shifter. We can change the phase along the transmission line. So if we have an open, we have one phase shift. If we have short, we have a different phase shift. And we can see that using CMOS switches, we can get something like 50% of the ideal phase change that this concept can achieve. And this is an example of that. So this is one example of something that we can do to control the properties. Another idea is to control the magnetic properties of transmission lines. So again, we have our transmission line, and we can embed inductors within that transmission line and control if we want those inductors to be shorted or open. If it's open, then it has minimal effect on the properties of the transmission line. But if it's shorted, then it would reduce the effective inductance that this transmission line sees. Okay? Or another illustration of that concept is that if we look at the transmission line as a series inductor and a shunt capacitor, something that if we solve the equation, we can show that this is an illustration of how we can transmit electromagnetic waves, then those embedded inductors actually form integrated transformers that are either open or short. And as a result, we change the effective inductance of those inductors along the transmission line. So this is an example of such a device. This is a transmission line, and these are the embedded inductors with the switches within. And what we can see is that if we change the voltage on the switch, then of course we go from open to short, and the phase shift changes. And we can do also digital control. We can change the number of switches that we turn on or off in order to get digital control over the phase shift in such a device. Do I have a few more minutes? 3 minutes. Okay. So the final example that I'm going to show is that can we actually synthesize a transmission line? Before we use some kind of basic real-life transmission line and change the properties, but in some cases we can actually synthesize the transmission line to have the kind of properties that we want or we need. So a natural transmission line would be something like I mentioned before, a series inductor and a shunt capacitor. And if we look at the dispersion ratio of such a transmission line, it's what is called a right-handed material, which has a linear dispersion ratio. And as a result, if we have different modes in that kind of transmission line, all the frequencies are going to be evenly spaced. And this is kind of a limitation if we want some reconfiguration and we don't want this even spacing of frequencies. So an alternative is to synthesize a left-handed material, something that can be created if we have a different kind of unit cell with a series capacitor and a shunt inductor. And then the dispersion ratio is nonlinear. And as a result, we can get different spacings of frequencies if we have multiple modes in the same transmission line. So we can't really synthesize something as ideal as what you can see here because of parasitics. So this is a more realistic model. So we have kind of a combination of left-hand, right-hand material. But we can use something like that. And in this example, we have 2 unit cells. Using this 2 unit cells of a left-handed material, we can have 2 resonant frequencies of this resonator, which are not evenly spaced. And we can use that within an oscillator circuit. This is the resonator, and this is the negative resistance that is used in order to sustain the oscillation in that resonator. And we use the CMOS switches in order to select the mode of operation. Do we want one frequency or the other frequency by controlling the phase from one point to the other that enables oscillations. So in this circuit, what we actually see is that we can generate either of these 2 frequencies that are pretty spaced apart. This is something like 20 gigahertz, and this is 55 gigahertz, using the same resonator and the same circuit by just using switching, selecting the mode of operation of our oscillator. And this is a picture of the actual chip. Most of the area is consumed by the inductors in the design. The transistors are too small to actually be seen in this picture. Okay, so to summarize, I've shown a multi-band RF interconnect as a potential candidate to solve the communication problem of future digital microprocessors using multi-band frequency generation circuits, on-off modulation, and on-chip transmission line. And we have seen some ways of using CMOS switches as a mean of controlling on-chip passive structures that can offer reconfigurable features to future millimeter wave circuit in CMOS technology. Thank you for your attention.
Thank you very much, Eran.
So you mentioned 60 gigahertz and 300.
Yeah.
How far can you go? Can you go to the terahertz?
Well, you can see that in the map. Actually, I think I showed that in the beginning. So it's just a matter of time, and you can really rely on that scaling trend. I think it was shown here, right? So I'm not sure. So you can see that nowadays we're more or less at 45 nanometers. So you can reach, let's say, 400 gigahertz. And in a few years, oscillators, transistors are going to be fast enough to reach into the terahertz region.
How does that make fundamentally? I mean, this will go forever.
Well, naturally it will not go forever, but forever can be a long time. Okay, so actually it's an interesting question because every few years people are going to say, okay, this is the roadmap, but in 5 years we have no solution. We don't know how to scale in 5 years, so no one knows what will happen after 5 years. And then 5 years pass, and a few billions of dollars are being spent, and a solution is found. So it's not going to be the same device. It's not going to be the same technology. But I believe that at least for the next 10 years, people are going to follow the trend. And usually it's even faster than predicted because of the pressure. I mean, the competition and the pressure. So things are even tend to be even. Even nowadays. We're maybe 2010 and supposedly 45 nanometer, but maybe not as a product, but definitely we have 32 nanometer technology already and some experimental 22 nanometer technology. So we're practically there. And what can also be done is that you can use a transistor that is not as fast as a terahertz, but use a fundamental source and then use harmonic generation. So maybe it's not a lot of power, but you can definitely generate above terahertz frequencies. Just a matter of how much power you actually need.
This is the frequency of a single transistor?
It's a kind of a figure of merit. I didn't want to go into the details because of the crowd, but this FT, it's actually the cutoff frequency of the transistor as a current amplifier. So it means that the maximum frequency that the transistor can actually amplify current.
So it's
and
not the switching frequency?
No, not a digital frequency.
It's the bandwidth?
Yes, yes. You can define that as bandwidth. But no one is actually thinking about switching digital circuits anymore at these high frequencies. This is not, I don't think that people really want to do that because of power.